Good morning, everyone. My name is Mehe bin Hamida, and it's a pleasure to present our research entitled A Self-Learning Multi-Objective Evolutionary Algorithm based on the Composition Framework using Deep Q networks for the Green Flexible Job Job problem. This work has been carried out in collaboration with Dr. Amani Azouz and Professor Lamjad Ben Said. Here is the outline of my presentation. I will begin with the context and motivation of our research. Then I'll describe the problem formulation. After that, I will introduce our proposed approach followed by the experimental results. Finally, I will conclude with key findings and possible directions for future work. In recent years, industrial production has been challenged by the need to achieve both productivity and sustainability. On one hand, manufacturers aims to maximize production and reduce delays. On the other hand, energy consumption and environmental impact must be minimized. This dual requirement has given rise to green scheduling problems which seek to optimize efficiency while reducing energy usage and emissions. One of the most widely used frameworks for solving multi-objective optimization problems is MOEA/G, which stands for Multi-Objective Evolutionary Algorithm based on decomposition. The idea is simple but powerful. Instead of solving the whole multi-objective problem at once, MOEA/G decomposed it into a set of smaller scalar subproblems. These subproblems cooperate with each other, which helps the algorithm achieve good results overall. This approach has two major strengths. It provides trunk inversions, meaning it can reach solution close to the optimal Pareto front, and it also maintains good diversity, ensuring that the solutions are well spread. However, there is a key limitation. MOEA/G is highly sensitive to static parameters, especially the penalty factor theta. Once this parameter is fixed, the algorithm becomes less adaptable when the search landscape changes. So the central question we raise is, how can we make MOEA/G adaptive? In evolutionary algorithms, a crucial aspect is balancing exploration and exploitation. Exploration allows us to discover new regions of the solution space, while exploitation refines the best solutions we already have, pushing them closer to the Pareto front. In the context of green scheduling, this balance translates into a trade-off between productivity and energy consumption. Several works in the literature have tried to address this. For example, MOEA/G 2 PPI, which uses two penalty values to key inversions and diversity, or adaptive operator selection strategies. Surveys also highlight this as a major challenge. However, to achieve true adaptability, we need to go further. Our idea is to introduce reinforcement learning and specifically Deep Q networks to dynamically adjust MOEA/G parameters during the search. Now, let me introduce the problem we are addressing, the green flexible job problem with speed variations. In this problem, each operation can be processed on different alternative machines, which give us routing flexibility. Moreover, machines can operate at different speeds, and this directly affects two aspects: productivity through processing times and energy consumption. So, the challenge is to manage the flexibility and variability while optimizing both production efficiency and energy usage. In our formulation, we consider two main objectives. The first is to minimize the max span or the total completion time of all jobs. The second is to minimize the total energy consumption. This problem has strong industrial relevance. It supports sustainability goals, aligns with the vision of smart and energy-efficient manufacturing, and directly addresses the trade-off between productivity and energy use. To model the green flexible job problem, we make the following assumption. All machines are available at time zero, and each machine can only process one operation at a time. Machines cannot be completely switched off before all jobs are done, but if they are idle, they enter standby mode. We also assume that increasing processing speed reduces processing time, but at the cost of high power consumption. Each operation must be executed without interruption, and operation within the same job must follow a fixed order. Finally, we consider transportation and setup time to be negligible. Now I will present our proposed approach, which we call MOEA/D GQN. It combines the strength of MOEA/D with penalty boundary intersection and deep queue networks. On the MOEA/D side, the problem is decomposed into multiple scalar subproblems, each associated with a weight vector and evaluated with the PPI function to balance convergence and diversity. On the GQN side, the idea is to provide self-adaptive parameter control. The agent observes the current state of the search, decides on suitable parameter settings, and learns over time which strategies lead to better solutions. MOEA/D provides the optimization framework, while the GQN adds intelligence by dynamically adapting the parameter during the search. Another important component of our approach is the cooperative mechanism. Every K generation, subproblems exchange their best solutions with their neighbors. These are evaluated using the PPI function, and the population is updated if improvements are found. This exchange encourages information sharing across subproblems, helps avoid premature convergence by keeping the search diverse, and ultimately improves both convergence throughout the Pareto front and the diversity of solutions. To integrate reinforcement learning, we define the problem in terms of state, actions, and rewards. The state includes the current penalty factor theta and the dispersion of weight vectors. The actions consist of adjusting theta to shift between exploration and exploitation and regulating weight dispersion to better control diversity. Finally, the reward is based on three aspects: improvement in max pain, reduction in total energy consumption, and diversity penalty that prevents premature conversions. This reinforcement learning framework allows the algorithm to dynamically adapt its parameter during the search. This figure shows the overall MOEA/D GQN framework. MOEA/D decomposes the problem and applies the PPI function, while cooperation allows subproblems to share solutions. The GQN observes the state, adjusts parameters, and learns from rewards, enabling the algorithm to dynamically balance convergence and diversity. For our experimental, we used a wide range of benchmark instances. This includes 6 instances from RandyMart, 17 instances from Huring et al., and 7 instances from Dozer, Perez, and Poli. To make them more realistic, we update all instances by adding variation in machine processing speeds, reflecting dynamic and heterogeneous environments. We compared our proposed MOEA/D GQN with the classical MOEA/D PPI, each executed independently 20 times. The population size was set to 200 with 500 iterations and a neighborhood size of 20. The theta parameter was fixed at 5.0. For operators, we used a crossover probability of 0.9 and a mutation probability of 0.3. This setting ensures a fair comparison between both approaches. To evaluate performance, we used 3 standard metrics. First, hypervolume. Second, IGD. Finally, spacing. This table compares MOEA/D GQN with MOEA/D PPI. Looking first at hypervolume, MOEA/D GQN achieved a statistically significant improvement with a p-value of 0.0366. This means our method provides better coverage of the Pareto front. For IGD and spacing, the p-values are larger than 0.3, so the differences are not statistically significant. However, MOEA/D GQN still shows slightly better average performance. Overall, integrating deep queue networks into MOEA/D enhances coverage and diversity, confirming the superiority of the proposed approach. This figure shows the hypervolume comparison across all benchmarks instances. As we can see, MOEA/D GQN generally achieve high HV values on several cases. In this work, we proposed MOEA/G GQN, which integrates DeepQ networks into MOEA/G. The key advantage of this approach is its self-adaptive ability to balance exploration and exploitation during the search. Compared to the classical MOEA/G PPI, our method achieves better hypervolume results, meaning that it integrates Pareto fronts that are both more diverse and better convergent. In the future, we aim to extend MOEA/G GQN to dynamic and high dynamicity problems, design stronger reward mechanism, and contribute to advancing adaptive optimization and computational intelligence.